All right, so here's an interesting molecule. It's a 7-membered ring with a nitrogen in it. Actually, sorry, it should be an NH. Just have a lone pair there. And is it aromatic or not, is the question, or anti-aromatic? Well, what do we have to look at first?
Well, we could look at the number of p electrons.
Yeah, you could sort of assume that maybe it is going to be aromatic and figure out if everything fits. So you can say, all right, well, let's say we know 7-member rings can be flat. So let's say it's flat, and let's count up the pi electrons. First check, does every member of that ring have an sp2 hybridization or have a p orbital that can participate in the conjugation?
Oh,
yeah. Yeah, they all can. The nitrogen can or cannot, depending on which hybridization scheme it takes, but it can have a p orbital with those electrons in it. Okay, so then if that's the case, how many electrons would this have? How many pi electrons would this have?
8 that's not the case.
Right, because if the nitrogen has, if you say that the nitrogen has a p orbital, if it's sp2 hybridized, then you're also saying that that lone pair of electrons is in that p orbital and thus a part of the pi system. So if that's the case, then there are 8 pi electrons overall, which makes it what? Yeah, well, the 8 electrons would make it anti-aromatic if it were flat. So what we would expect is that this molecule is actually not flat. It twists out of being flat so that those electrons aren't all in a pi system together, but rather they're individual triple bonds. Right. So this molecule overall should probably be considered anti-aromatic in the context of assuming it's flat. But in real life, and we don't know about this, it will either bend so it's not anti-aromatic, or it just doesn't exist.
Since the book would say this is non-aromatic.
Yeah. Yeah, but you only get to that conclusion by first realizing that if it were flat, it would be anti-aromatic.
Sure. But I mean, at least like the section describes it as you're supposed to rationalize this as being non-aromatic because it will adopt a
yeah.
counter. So
right.
What would be an answer on the test?
So on a test, I would have to be more specific. I would say assume it's flat.
Okay.
Right? Or I would say, would you expect this molecule to be flat or not? And you would say, I would not, because if it were flat, it would be anti-aromatic, so it must bend out of that. So anti-aromatic, which really means that it ends up being non-aromatic.
Also, I have a question.
Mm-hmm.
How many peaks on a carbon-13 would you show?
Okay, let's talk about that. Yeah. So that would be, let me make sure I got it right, like this?
Yeah.
Okay. So here's a tri-substituted benzene. How many peaks on an NMR, on hydrogen and carbon, would you expect this to show? Well, let's look at hydrogen first. First, let's look in the non-aromatic region, right? The non-aromatic hydrogens. Which peaks would we expect to see? How many peaks would we expect to see in the non-aromatic spectrum?
You'd see one because all three of those are the same. Those methyls.
They would all be, technically they'd all be close to each other, but they'd be different. Yeah,
that's right. So you'd expect to have 3 close, potentially even overlapping, around somewhere between 0 and 3, let's say.
And those would be individual peaks, right?
They would be individual peaks. They'd be singlets. They'd be 3 hydrogen singlets. They may be so close that, in fact, they seem to overlap. But they are indeed different. You can look, you can name this molecule. You can call this molecule, well, what would you call this molecule?
You call it 1, 2, 4 tri.
Yeah, you probably call this 1, 2, 4 tri.
The shortest numbers. You also call it you also call it 2,4 dimethyl toluene.
Yeah. Yeah, that would be acceptable also. This is probably a little bit better name because there's no reason that one should be, like, have priority over the others and become, but anyway, yeah, that's fine too. In these numbers, so if I wrote 1,2,4 trimethylbenzene, just the word, and I asked you to write the structure, you could write that structure and we could all agree on the exact same positions of which one's at 1, which one's at 2, and which one's at 4. So that means that those positions are all actually different. And that's why we see 3 separate peaks, not 1. Okay. So what about the aromatic region? What would the aromatic region look like in this? First, theoretically, and then we'll talk more in reality. But theoretically, what should it look like? Well, that's probably in real life what it would look like. But if we look theoretically based on the splitting, what should we see for each hydrogen? In other words, are these 3 hydrogens, we'll make them red, blue, and green. Sorry if you're colorblind. Would those hydrogens all be in the same group? Would a couple of them be in the same group? Would they all be in different groups? What do you think?
The 2 on the bottom would be in the same group.
Why?
Because they're indistinguishable.
Are they though?
I think.
No, so you're gonna have 2 peaks.
Why?
3 different peaks.
Why are the 2 on the bottom? Why do you think they're not? They are distinguishable.
Because the one hydrogen is closer to the 2 methyls on top versus the one on the bottom. They're not identical in location compared to the substitution we talked about.
That's right. They are in extremely similar chemical environments, but not identical. In other words, this one is next to, you could say, the 2 methyl groups, and 2 away from the single, and this one is close to this one and 2 away from those. So you can tell them apart. However, those 2 environments should be very similar, ultimately. Okay, so what about the splitting? Let's look at the red one first. What do you expect that peak to possibly look like? Well, maybe not.
Well, I mean, it could be a doublet.
In fact, that one's going to be a little bit potentially complicated. So this could be split by this green one in metasplitting, and then also potentially split by the blue one in parasplitting, which we would expect to be much smaller. So it's actually, we would expect to see a doublet of doublets, maybe a very small splitting from the para, and then a slightly bigger one from the meta. Now let's look at the blue one. Now this one, we would expect to see ortho-splitting from the green one and para-splitting from the red one. So if we're saying that para-splitting is this tiny little split here, and ortho-splitting should be bigger than meta-splitting, this peak might look something like this.
Wait, so the red one looks like that because why?
Because it doesn't have any ortho neighbors, it only has meta and para. And then the green one, we would expect to look a little bit different because this one should have both ortho-splitting that we see here and meta-splitting, but not para-splitting. So it won't have that real thin splitting. It'll have the other two. Whoops, that's not green. So it might look like this. Right. Well, okay, so it's not exactly drawn to scale, but let me annotate this for you. We'll say that J1 is from ortho-splitting. These are coupling constants. J2 from meta, and J3 from para. So what we see is this distance here is J2, that's the meta-splitting. And this little distance here, that's J3 from para-splitting. And this big one is J1 from ortho. Again, J3 from para-splitting. And then what we see down here, even though it's not to scale, this is J2 from the meta-splitting. And even though, again, it's not to scale, this is J1 from the ortho-splitting. So if we could distinguish those three hydrogens in the NMR, and if you had a suitably high-powered NMR, you could do that. This is what we would expect those peaks to look like. On a normal everyday lab NMR, it's probably all lumped together and really looks like a multiplet because those hydrogens are also similar in chemical environment. So let's check this out. One of the reasons you'll notice that one of the reasons that we do the nitration experiment as opposed to some other aromatic reaction is that electron withdrawing groups tend to exaggerate this difference and spread the peaks out and make the coupling constants much larger. So when we have nitro groups on molecules, the splitting tends to be more obvious, and that's why you can see it in your NMRs from lab, but sometimes you can't with other groups on there. So as an experiment here, let's actually look this up and see if we can find it. There's a pretty neat website called the Spectral Database for Organic Compounds out of Japan. You can actually look these things up. So we can look up trimethylbenzene, see if we can find the one we want. Uh, 1,2,4 trimethylbenzene. We can look up the hydrogen NMR.
Wow. This is awesome.
And so it's not a great picture. It'd be nice if they had a little higher resolution one, but we can certainly see this. And in fact, kind of what we predicted is true. You see D, E, and F peaks all right around 2.1, but they're all kind of clustered together. It's not really clear that one seems like a little bit separate. That's probably this one. And then E and F are pretty much right on top of each other. And that's what we see here. You can see the numbers here. And the same thing with the aromatic peaks. If we could zoom in on that, if it were a more higher resolution spectrum, we may be able to see some of that splitting that we described. But they're so close to each other that they're basically right on top of each other, and it more or less looks like a multiplet. So for this particular example, we probably won't see that kind of splitting. And here we could actually replot the original data if we wanted to, but we won't get into that. All right. So this is a really useful website if you ever need to find spectra. It's a weird website, but like the address is hard to write down. But if you just look up SDBS in Google or some other search engine, you'll probably find it. That's how I usually get there. And this was done on a 400 megahertz NMR. Ours upstairs is 90, so our resolution will be even less, and you'll just really just see everything right on top of each other. All right. Other questions about that?
Yeah, carbon 13.
Oh yeah, carbon 13. So let's talk about that. How many signals would you get in the carbon NMR here?
Luke says 9.
9. Do you agree? So every carbon atom in this molecule is in a different group or is chemically distinguishable from each other?
I don't know. I don't know how to.
Well, let's look at those 3 methyl groups again. Can we determine them one from another? Can we distinguish them?
Yes.
Yeah, we can, because we can number them 1, 2, 4, and no matter how you draw that, how you rotate it, how you flip it around, there's never a question which one's 1, which one's 2, which one's 4. Now, if we removed one of these methyl groups, then the other 2 would be indistinguishable. But having 3 of them there gives it enough asymmetry that they are actually distinguishable. And so it's the same thing then with the carbons in the ring. You expect to get separate signals from each of those carbons as well. But, again, they should be very close because they're very similar chemical environments, even though they're not identical. Let's look at the website again, see if we're right. Okay, so this is actually well distinguished. Right? These 3 are, 2 of them are right on top of each other. 8 and 9 probably are right on top of each other. Yeah, one's at 19.61 and one's at 19.19. So those are not going to be really, you're not going to really tell that. But all 6 of the aromatic peaks are actually kind of distinguished. Now, which one's which? That's actually an interesting thing that we haven't gotten into, and we won't now. But it has to do with which groups are electron withdrawing or electron donating, and how that determines where they end up based on what type of an atom or what type of a resonance form can be stabilized with the charges and all of that. So that's where they actually assign each individual carbon on the ring. We won't get into that. Any other questions about that? Okay. So aromaticity, NMR, those are good things to review. Certainly the reactions, and we'll get some of those on the exam or on the quiz on Wednesday too. Other questions about that? Or should we move on? I guess. All right, let's move on. Next part, actually. All right, so now it gets into the second half of the class. Which is the entire rest of the semester is going to be concerned with the chemistry of the carbonyl group. That is C double bond O. We're going to talk about aldehydes and ketones. We're going to talk about acids, esters, amides, all that kind of stuff. And then we're going to talk about what happens to stuff around the molecule when there's a carbonyl group there, and something forming called enolates. So we'll start with aldehydes and ketones. We've seen these a bunch. Of course, we've used them in lab. We've done stuff with them. We've talked about them. We've made them, actually, on paper. We haven't totally discussed the whole point of this, though. So let's first discuss what makes a carbonyl group so special and why we need to devote half a semester talking about its chemistry. What is it about the reactivity of a carbonyl group that is special? Special is kind of a broad term, but how do you think a carbonyl group reacts?
Well, it can react both as a nucleophile and electrophile.
It can react as a nucleophile and electrophile. Most of what we're going to talk about, for a while anyway, deals with it acting as a electrophile, and very specifically, an electrophile with the following separation of charge. Okay? So there's a dipole moment there that exists between the carbon and the oxygen, which means when it acts as an electrophile, that means a nucleophile is attacking the carbon. And that's primarily what we're going to deal with in the next few days. Now, when it's acting as a nucleophile, the oxygen is attacking something else, and we'll deal with that a bit as well. We can also see this in a resonance form, where there is actually a full separation of charge. Not a hugely important resonance form, but one that exists nonetheless, where you actually see that separation of charge. And so this is the type of thing that is how it's going to react. Now, the other reason we spend so much time talking about it is that these things are everywhere, much like alcohols, but their chemistry is a bit more complicated. So alcohols, I would say, are arguably a more important functional group, but their chemistry isn't as important. When it comes to biological things, though, carbonyl group plays a close second, or maybe is even tied. So here's some examples of important aldehydes and ketones. Flavor molecules, things that you taste, often have, and smell, often have aldehydes in them. Aldehydes are kind of stinky, sometimes really in a bad way, and sometimes in kind of a nice way. Hormones and other biologically important molecules tend to be ketones. In fact, anything you know that is a biological molecule that ends in -one does so because it has a ketone. That's where that comes from. So hormones, progesterone, testosterone, steroids tend to end in -one. Those are also important. And then some industrially important ones that I don't know, you probably haven't used much formaldehyde, but certainly acetone we've used plenty of, which is a ketone. And we'll do some reactions with acetone as well. Okay, so let's talk about these naming things. We're not going to get too into all the fancy special rules, but you should at least have an idea what these things look like and what they're called. So does anybody know how you would name this molecule? Yeah.
Butane with Al.
Yes, butanal. So we kind of exaggerate that al to separate it from the all of the alcohols. But yeah, this would be, it's got 4 carbons, so it's butanal. And this is, in fact, the proper systematic way to name aldehydes, is to take off the suffix and put al. Of course, we're going to see exceptions for common aldehydes, and for where the aldehyde is actually not a part of the parent structure. So in this one, we can't really call this benzal. That doesn't really make sense, because the aldehyde is on a separate carbon from the benzene ring. So just using a suffix on the benzene doesn't really tell us that the aldehyde is in fact on another carbon. So because of that, this one's called, as you know, benzaldehyde. Same deal here. We can't call this one cyclohexanal, because that would imply that the aldehyde is somehow part of the cyclohexane ring. To get around that, then, we call this cyclohexyl carbaldehyde. And that carb tells us that, in fact, there's another carbon there that has the aldehyde in it. Whoops, it's actually cyclohexane carbaldehyde. cyclohexane carbaldehyde. All right, some ketones then, named very similarly. Of course, you know acetone. I don't think we need to put that one on here. Sometimes the ketone is simply named based on where it is in the chain. That's never an issue with aldehydes because the aldehydes always have to be at the end. But with a ketone, this one is a pentane, so we would call this 2-pentanone.
I got a question.
Yeah.
You just say pentanone and saying, like, because obviously if it's a ketone, it has to be in the, it can't be at the very end. So if you put pentanone, would that be a default that you have? It would just be at the lowest possible.
No, in this case you have to specify that. Whenever there's more than one ketone possible, you should specify where it actually is. So that's 2-pentanone. This one's 3-pentanone. So just to avoid confusion, we always specify that. You can have cyclohexanone, where the ketone is not coming off the cyclohexane, of course. And then the old kind of non-systematic way to name ketones is to name what is on each side of the ketone. Like this one, what would be the systematic name of this? Well, this is a ketone. This is a ketone. And the systematic name would be to look at the chain and see it has a 1, 2, 3, 4-member chain with 2 methyl groups coming off here. So it should be 3, 3 dimethyl 2 butanone. However, the common name of this might be methyl tert butyl ketone. That's not systematic. To name it kind of like an ether with one thing on each side. So if you see these things as solvents, like ethyl propyl ketone or methyl tert butyl ketone, MTBK, sometimes those old names are used if it's a chemical that's been around for a while. But this is really the systematic name. These molecules are relatively polar. If you think about a solvent like acetone, acetone's miscible with water, but it'll also dissolve a lot of organic stuff pretty well too. So they're pretty good kind of middle-of-the-road solvents. Their ketones are great for dissolving things like acetone, like cleaning things and all of that. They're often not as good for doing reactions and that sort of thing because they're also reactive. So you can't do a lot of reactions in ketone solvents, but you can use the ketone solvents to dissolve a lot of stuff. All right. I think that's all we need to talk about ketones or with these. I'll give you one challenge problem here just to see what you remember. This one's from the book. I think it's a pretty good question. What is the name of this ketone? And don't forget stereochemistry. So what's the parent of this? It's a heptanone, right? Because it's got 1, 2, 3, 4, 5, 6, 7 carbons total. So this is going to be a bicyclo 2,2,1 heptanone. Now, how do we indicate where the ketone is? How do you number these things? It's 2, that's right. You start at a bridgehead, which is where these things come together, whichever one is going to give you the lower number, and then you start numbering around either the largest ring or toward the functional group. So this is going to be 1, 2. So that's going to be 2. Actually, it's probably clearer if we put it in here. All right. Is that it? No, because we have to account for stereochemistry. So where are the stereo centers?
The bridge has, right?
Yeah. So carbon 1 is a stereo center, and carbon 4 is a stereo center. And what's the stereochemistry of each of those? Well, let's look at them. So this one, the hydrogen's already in back, right? Because the hydrogen goes back here. So this is going to be first priority. This one's second. This one's third.
Why is it second?
Because if we, so we know that one's first. Those two tied. So then we move to the next one. And this has more carbons connected to it than this one. So it's S. So this is 1S. And then 4. We've got 1, again 2, and then 3, but it's the opposite, so that's 4R because the hydrogen's coming out at us. So 1S, 4R, bicyclo 2, 2, 1, 2.
Wait, so what is it? 1 point, or is that 2.0?
That tells us that it's a bicyclic structure with 2 carbon group, 2 carbon group, and a 1 carbon group. So it's got 3 different parts that connect together at the bridgeheads of that many carbons each.
Wouldn't it make more sense if it was 2, 1, 2?
Yeah, but it's by convention you always do it in decreasing order of numbers. Because it just talks about the connectivity, not doesn't matter how one is connected in order of the other. All right. Okay. Moving on then. Let's talk about some reactions. Now, since we've already done them pretty much all this semester, actually, which is different from how we've done it in the past, that's good. I think we don't need to spend a whole lot of time on the preparation of aldehydes and ketones. Because I don't think we're going to talk about any new ones at all at this point. Because we've already done them all. So let me just show you a quick summary of them. Aldehyde preparation. Of course, you can oxidize primary alcohols. You can break up alkenes in ozonolysis. Or you can hydrate terminal alkynes. Probably the first one here is going to be the one we use most to prepare aldehydes. Ketones, we've got basically those same things, plus one more, which is the Friedel-Crafts acylation we talked about last chapter. Okay. Any questions? All right, you guys know those. So now that we know how to prepare the aldehydes, let's talk about what we can actually do with them. Now, some of these reactions we've also already talked about, but I want to be a little bit more precise at what's going on here. So you'll recall a few chapters ago, we looked at things like this, right? And what did that mechanism look like? How do we draw the mechanism of borohydride attacking a carbonyl? Yeah.
It's gonna protonate the carbon.
Well, it's going to attack the carbon. Yeah. Yeah, essentially, right. Technically, it's not a protonation because the hydrogen is a hydride, H minus, but you're right, yeah. But we said this kind of acts as a hydride, and it attacks the carbon like that and leads to this kind of an intermediate. Now, essentially, that's the whole mechanism of these next couple chapters. That's what's going to keep happening. Things attack aldehydes like this, and the only thing we're going to change is sometimes it's an acid or sometimes it's in base, and that will move things around a little bit. Let's talk about the stereochemistry of this addition. Is this a stereospecific or stereoselective reaction? That is, does something in the starting material control the stereochemistry of the outcome? Or is it something that you're always going to get a mixture of products? Yeah.
The substrate will determine the
Stereochemistry. How?
Well, I mean, if you have two different groups on either side of the ketone.
Okay, but will it favor one over the other? I guess is what I'm saying.
Like if it's attacking.
Yeah, will that hydride preferentially come in from the front or from the back for some reason or another?
No.
Probably not, right? We'll see some exceptions of that. Well, we probably won't see them, but you might see them in a later class as you go on with your inevitable chemistry majors that I'm sure you will all be taking. But really what this is, I'm not going to attempt to draw this. Let me just show you. It looks like this. So the nucleophile comes in from either the top or the bottom of this. And I'm going to copy this so we can play with it a little bit. Okay. So the nucleophile can come in from the top, and I would say, or from the bottom, because essentially this is a flat substrate. Now, when these R groups are very, very large and oriented in one particular way, sometimes you could imagine that you sort of force a nucleophile to go to one side or the other. But in general, it's going to go both ways, and you're going to get a mixture of products. So you would expect to get this, and you would expect to get whatever that nucleophile is, this. And in each case, no matter what we're doing here, we're making this tetrahedral intermediate. So I'm going to often talk about the tetrahedral intermediate. And that's what this is. That's what these are. And it's just saying that's after something is attacked to carbonyl, that intermediate, whatever it is going to be tetrahedral. It's sp3 hybridized. Okay. So based on that idea, which is more reactive? A ketone or an aldehyde? And why? So now that we know the mechanism, what do you think?
Aldehyde.
Why?
Because it's less certain.
Okay, yeah. So one part of it, there are actually two reasons here. And if you're noticing a pattern, this is always the two reasons. You've got steric reasons for things happening, and you've got electronic reasons for things happening. Steric is, of course, about what has room and what fits in where. Electronic is things like resonance, which one's more negative or more positive. So first, there's certainly a steric effect here, where the aldehyde is less crowded as that nucleophile comes into the carbon. There's also an important electronic reason. So using things like more negative, more positive, more nucleophilic, more electrophilic, using those sorts of words, can you find a way that also applies to these, either in the same, either favoring the aldehyde or favoring the ketone? What is the difference electronically between these two species?
The aldehyde, there's a greater electrophilic being distributed as well as with the R groups. As with the
Yeah.
other groups.
Right. So, as we talked about last chapter, alkyl groups can be partially electron donating, right? Not a lot, but they're partially electron donating. There's a bit of a dipole there. So these help stabilize that carbonyl carbon, make it less positive. So in this case, the carbonyl carbon, well, let me just do it with an arrow. In this case, this is less positive than this one, because it's being slightly stabilized by those R groups. Now, is that an enormous effect? No, I don't think it's an enormous effect. But it's an effect nonetheless. And those two things taken together mean that overall aldehydes are going to be more reactive generally. So in the electronic effect is that the carbonyl carbon is less positive or less electrophilic in the ketone.
Does it matter if the ketone has a bigger R group? I mean,
Sure.
compared to the aldehydes?
Yeah. So you can imagine examples where a very, very large R group on an aldehyde might actually end up making it more hindered than a small group on a ketone or something. But in general, most aldehydes are relatively unhindered because they always have to be at the end of something. There's just a hydrogen on one side. Okay, so moral of those stories. Aldehydes tend to be more reactive. Okay. That's going to come up in a bit when we start talking about synthesis. But before we get into those reactions, let's talk about the general mechanism. And this is very important because we're just going to keep doing this over and over and over again. And if you think about it in this way, every reaction we talk about, pretty much, with the exception of a couple weird ones, is just going to use these sequences of steps. So you've got basically two possible mechanisms of carbonyl addition. And one we've already seen. If it's in base, strong bases, then what you're going to have is nucleophilic attack followed by proton transfer. Remember those steps from the way back in the book where it kind of broke down into a different couple steps? So in basic conditions, you have nucleophilic attack followed by proton transfer. And that's the one that we've already seen. So that's like, you've got this, you've got your nucleophile that has a negative charge probably because it's in base. All right, it attacks. You've got your tetrahedral intermediate. And then in your second step, you've got water or whatever that you add in to protonate it. Could be some other type of protic thing, but something like that. So you got a nucleophilic attack, and then a proton transfer. That's what we've done already. Now this one we haven't done yet, and that's the acidic conditions. Very similar. We're just going to rearrange the steps a little bit. Now in acid, we don't tend to have negatively charged nucleophiles floating around. We have neutral nucleophiles. So in acidic conditions, and I'm going to use a more specific example this time, I'm also revising what the book says a little bit, because I think what the book says is a little bit misleading in this when we get to it later. In acidic conditions, what's the first step always? Proton transfer or protonation. Yeah, so proton transfer. And then we have the nucleophilic attack. And then usually there's a third step of deprotonation. So that looks like this. We'll have something like acetone in something like water. Now water in acidic conditions is hydronium, right? So the ketone will first get protonated. That's the protonation part. Then we'll see the nucleophilic attack by whatever nucleophile, in this case, maybe still the water. And notice that attack still looks the same. Then you have your tetrahedral product. And now, that's probably an okay product in an acidic solution. But if we really want to talk about a neutral product that we would ultimately isolate, that's where this final deprotonation would come in. Right, so another molecule of water might deprotonate this so that we have a neutral product. Now, this is probably the most important thing we're going to talk about in this chapter, because literally for the next couple chapters, this is what we're going to do. Just over and over again with different specific examples, but the same mechanism. So why do this acidic one? Why does that have to be a little bit more complicated? Well, in the acidic conditions, okay, we know the sort of convention that you always protonate first. But why do you always protonate first? Why specifically in this case do you protonate first? And I'll ask you that. Why is it important? Why do you need to protonate that carbonyl to get this reaction to go? Why is that important here?
Obvious reasons we have 5 bonds. We didn't have that carbonyl group flipping the electron.
Sure, but what if, I guess why doesn't a water molecule just attack the carbonyl and then cause the electrons to come up and have like a negative charge on the oxygen? Why not do that first and then protonate it? Okay. Well, it's actually has to do with the reactivity of the carbonyl group. Carbonyl group is reactive, okay, but it's not reactive enough to react with a regular old neutral nucleophile like this, generally. So what happens is this thing is very electrophilic. you can imagine that, yes, it's resonance stabilized, but resonance where that carbon shares the positive charge. So that those things together, that's extremely electrophilic. When a carbonyl group gets protonated, it's much more reactive toward nucleophilic attack than if it were just a regular old neutral carbonyl. And that's why we see that happening in acid. Okay. So what we're going to talk about now is some specific examples of these very mechanisms. So first example, well, we'll kind of put these in categories. We'll first talk about what happens when you do this with oxygen nucleophiles. That's basically what we just saw. So if you react a ketone or an aldehyde with water, there's an equilibrium that leads to a hydrate formation. All right. And you can do this in acid or base. And it's an equilibrium. But depending on what the substrate is, you can favor one or the other. So the hydrate is not usually a product that we actually want for anything. It doesn't stick around much. But it's useful to know that it's there. For instance, I don't know if you've ever noticed this, but if you take an IR of a compound with a ketone, you always see some water-looking peak. You always see some OH peak. And maybe it looks to you like there's water in your sample, or it's not dry or something. But in fact, this is what's going on. You're always seeing some hydrate in there, just from the ketone or the aldehyde absorbing stuff from the air. And in certain aldehydes, certain small aldehydes actually favor the hydrate, and you may not see the ketone at all. That's interesting from various standpoints. We're not going to dwell on it because both actually, because of the equilibrium, they react the same way. So it's just to know that this actually does happen. Right? A more important version of this, a more important version of the oxygen nucleophiles is what we call an acetal. And that's what happens when a ketone or an aldehyde reacts with an alcohol. So you react this with two equivalents of alcohol in some sort of an acid catalyst in the presence of acid. And you get this. A common acid that you'll see as catalysts, TSOH, toluene sulfonic acid. That's like a tosylate but protonated. Right, so it's this thing. Now that we've talked about sulfonic acids and orthometaphora stuff, you know, para-toluene sulfonic acid, that's what this looks like. And then sulfuric acid, sometimes used. Para-toluene sulfonic acid is a great acid for this because, well, either of these, because neither one is nucleophilic. So it can give a hydrogen without having a danger of attacking instead of the alcohol. Right. Okay, so let's, rather than just kind of go through the mechanism, let's try to figure this out together. Why this happens the way it does, based on those mechanisms that we just saw. And then we'll be done. So we're going to react this with, let's say, ethanol and TSOH. What's the first thing that happens? Protonation, right? We're in the presence of acid. So the first thing that's going to happen is we're going to protonate. This also tells us that this entire mechanism is going to go via the acid catalyzed type addition that we just talked about in the previous page. Okay. So what's next? Nucleophilic attack, right. What attacks? That's right, the ethanol will attack now. Okay, so what happens next? That's right, and in fact, it's a, in this case, it's going to be a proton transfer up to here. So it's sort of like a deprotonation and a protonation in sequence. So let's actually, well, what does your book do here? Yeah, the book does them separately, so we're going to keep it separate too. So now we've got some kind of a base, maybe water or more ethanol. There's no water here actually, so let's just say ethanol. Is going to deprotonate. And now, since we know we ultimately have to get rid of the alcohol because this is our product, what happens is that that OH now gets protonated. All right. And now here's the only part that is not kind of described in the mechanism before, and that's just because we don't actually have a carbonyl here, right? So this is another part of the mechanism. What happens now is you've made water here, right? Water is a very good leaving group. So we reform a type of a carbonyl as the water leaves. Okay. Now look at this intermediate. That's going to be a highly reactive carbonyl, kind of like the one we talked about before, the protonated carbonyl. But this is even more reactive because it can't be deprotonated. It's actually got this carbon stuck on there, and that ethyl group certainly isn't going to leave on its own. So what happens now is you have a highly activated intermediate which gets attacked by another equivalent of ethanol. And then water or whatever base is around can deprotonate this, and you end up with your final product, which is the acetal. Okay. This is known as an acetal. One other part we should name here when this thing is halfway done, is right here. So you have the ethoxy part here, but you still have an OH also. That's known as a hemiacetal. Hemi means half, so it's sort of halfway there. And hemiacetals have some importance, especially in carbohydrate chemistry, which we'll get to later in the semester if we have time. All right, so that's the final acetal. What we're going to do next time is talk about how this goes backwards. It's actually reversible. And that's the great synthetic utility of the acetal, is you can put it on, you can take it off, and it completely changes the reactivity. Carbonyls are highly reactive to strong bases, like Grignards and hydrides. Acetals are not reactive to strong bases. So you can use that to actually protect aldehydes and ketones from reaction in those ways. So we'll talk about that on Wednesday.